Alright, gentle reminder, quiz 16 is due tomorrow, PA7 is also due tomorrow. And for the first hour, we're going to go through RDT still, TCP's RDT. And we'll go over the finite state machine of TCP's RDT, the simplified version, and then the more realistic version, and then lastly the 2 extra hacks in RDT so that we could transmit a bit more efficiently. And then quiz 18 will be coming up. And here, RDT of TCP. These are the characteristics. First of all, it's pipelined. So we send packets back to back in TCP as well. We could have multiple packets in one flight. And the acknowledgement is cumulative, meaning the sequence number in the ACK indicates all the packets below that up to that number are received correctly. And there's only one retransmission timer for the entire flight of packet. And so when that timer times out, then we retransmit the flight of packets. So up to this point, you will probably guess TCP's RDT looks very much like, GBN, the go back in. Now the slight difference is this. In TCP, the RDT adds a little bit something so to speed up the retransmission. And that is a special condition when the sender sees a certain number of duplicate ACKs arriving quickly. Yeah, retransmission timeout, that's not wait for that, that's quickly retransmit. Okay, so this is also called the fast retransmission mechanism. So this is something that's a little bit unlike the standard go back in, but implemented in TCP. Right. Next are the finite state machines of the TCPs. To make it simple, let's ignore the dupe ACK part, okay, the fast transmission part, and let's not talk about the other mechanisms we have not yet discussed that's implemented in TCP. If you are expecting TCP sender looks very much like go back in sender, you're correct. First transition is what? The get call from above transition. Okay, receive data from application. Okay. So in TCP sender, we generate the packet, assign the sequence number to the packet, of course also calculate the checksum, and pass that to the lower layer. So it's essentially the UDT send call. And we check whether the timer has already been started for the flight. If it does, don't do anything. Otherwise, if there's no timer currently running, we're sending a packet, then this must be the send base. Start the timer. And then we increment the next seek num. But in TCP, we are not counting packets, right? If we are counting packets, we add the sequence number by one packet. But here, we are counting the bytes. So we are adding the number of bytes in the data in the packet we're sending out. Now, you see here, I'm trying to be a bit lazy. I did not do the window size check, okay? But in TCP sender, there's also a window size. So there should be an if condition here before creating packet to check whether the next seek num, okay, is still within the window limit, of course. And next, this is also a familiar transition. This is the transition when the sender receives an ACK. Well, similar to go back ends, transition receiving an ACK, that's extract the sequence number from the ACK packet. Now, the action of TCP sender here is different. Only when the sequence number is larger than the send base, meaning this is a new ACK packet. So the sequence number here is something that has not yet been acknowledged. Then we set the send base to the new sequence number because now acknowledgement is received. Sender should say that that's slide the send base over. Now, if there are currently not yet ACK packets around, then that's restart timer. So we'll be starting the timer for the new send base. if there are no outstanding packets, so if there are no not yet acknowledged packets around, then let's simply stop the timer. Because this act here, acknowledges all the packets that are waiting to be acknowledged. Right? So, hey, looking very simple. That is also saying when y here equals the same base, we do what? Nothing. So if a duplicate ACK is received at the TCP sender, hey, timer does not get restarted, unlike in go backend. Even though the sequence number is the same, timer gets restarted, refreshed. Okay. And the third transition, again, very typical, this is the timeout transition. So when timer times out, retransmit the entire flight of packet from the send base, and then start timer. This is actually identical to go backend. In go backend sender, there's actually one more transition, which is doing what? Checking whether the ACK is corrupted or whether the ACK is a NAC. Okay. In those cases, we do nothing. But you see, when ACK is received, do these. And when the ACK is new, is doing this. So all these other things do nothing, is just, saying default actions all ignored. Okay, so from now on, if you don't see any other conditions being listed as a transition here, that means they will be just ignored. Now, this is just another way of writing the finite state machine, but in a pseudocode form. So we switch different events. There's the data received from above case, there's the timeout case, there's also the receiving of an app packet case. So receiving data from app, generate packet, set the sequence number in byte count, and start timer if there's not one yet running. Just to make sure that you set the timeout interval to what? The estimated RTT plus 4 times the deviation of RTT. In timeout here, if it is triggered, then retransmit the whole flight of segments and restart timer. Receiving an ACK, extract ACK number. If the ACK number is new, meaning it's acknowledging something that has not yet been acknowledged previously, then update the same base. So we slide the window over. We restart the timer if there are still unacked packets waiting. Otherwise, stop timer. These are the only 3 events. If there are other events occurring not fitting any of these events, ignore. If you're not quite convinced, the previous slide is the pseudocode. This one should convince you. Okay, so what I'm listing here, typing up here, is essentially what the finite state machine is telling. Initialization, and this, it's gonna go forever. It's looping forever, just like every server here, right? Waiting for an event to occur and take the actions correspondingly. It's a switch essentially on the events, and there are 3 different events. Getting data from above, timeout, and receiving an ACK. So, from a finite state machine, you can actually convert it to a pseudocode, give this to your programmers, then you get yourself a TCP sender implementation. Right. So, being able to write out from the thinking, from the designing of TCP sender to the finite state machine is essential because, that drawing the finite state machine out of your thinking process is simpler. Okay? Trying to write the pseudocode out of the state is just too challenging. Okay? Once you get the finite state machine, then you can gradually transition that to pseudocode. And there, you are one step closer to getting an implementation of what you were thinking about, what you were designing about. All right, so that was TCP's RDT, finite state machine, all the way to the pseudocode. But that was a very simplified version if you recall in the introduction. As usual, let's walk through a number of examples and exercise our understanding of the TCP's sender-receiver mechanism. So first scenario, very straightforward. We do have a data sender here. Host B is just receiving, sending acknowledgements. Host A here sends 1 packet starting from sequence number 92, It's carrying 8 bytes of data. Therefore, the ACK should be carrying the sequence number 100. Now, this ACK packet is lost. Okay, so host A here waits until timer fires. And so the same packet is retransmitted. Finally, ACK comes back, and the next packet will go out carrying sequence number what? 100. Because the ACK number here is counting to the last byte plus 1. So 92 is the first byte. The last byte will be plus A subtracting 1. But ACK is adding 1 back here. Right, so it's 100, and adding 1 back is also a way for the receiver telling the sender what is the next byte expected, what is the next data byte expected. So the packet coming out from the sender next is definitely going to be the same sequence number in the ACK received previously, right? 100. And the second example, again, host being the data sender, host B being the receiver. This time host A sends 2 packets back to back. First, starting from 92 and then carrying 8 bytes of data. So we know that the last byte is 99, therefore, the second packet starts from 100. And 20 bytes of data to be carried, so the last one is what? 119. And therefore, the ACK packet for the first one is last byte plus 1, 100. The ACK packet sequence number for the second packet is last byte plus 1, 120. Now, in this scenario, we are trying to demonstrate the strengths of using cumulative DAG. That is here. If one of the back-to-back packet that came in earlier, ACK is lost. But as long as one of the later one arrived, because 120 here is saying, server, you know what? All the packets before the sequence numbers are acknowledged, whether you receive an ACK packet for an earlier sequence or not. So up to this point here, sender host A here seeing, ACK 120, and therefore this packet and this packet both acknowledged. Okay. Therefore, there's no timeout is going to occur, and it's going to trigger sending of the next packet starting from 120. The third example scenario looks very much like example 2's, where we have a sender sending 2 packets back to back. Sequence numbers identical. Therefore, receiver here will be sending back ACKs, 100 and 120. The difference is this. Example 3 is to demonstrate a case where we have premature timeout. So that is saying the timer here, the interval is set very short. So timeout occurs before ACKs can come back. So first, timer occurred here. Therefore, timeout event in TCP sender's trigger. Therefore, we retransmit all the packets in the flight. So sequence number 92 will be retransmitted. Sequence number 100 will also be retransmitted. Okay. Now, ACK 100, ACK 120 will arrive later. Okay. So when ACK 100 arrive at the sender here, Y equal 100, that is the sequence number in the ACK. The same base at this point is still 92. So Y is greater than same base. Therefore, we change the same base to the new ACK number. And do we restart timer or stop timer here? Well, there is still outstanding packet, right? Which is this one. So we cannot yet stop the timer. So timer is refreshed here. So timer for 92 is restarted here because, timeout occur, retransmit everything, start timer. So there's already a timer ticking starting from here that is associated with sequence number 92. But here, we restart the timer, and this timer is associated with same base 100. When ACK 120 arrive here, we need to change the same base because it was previously 100, and the Y is 120, bigger than 100. So change the send base, slide the window over. Do we stop timer or restart timer? Well, there's no more outstanding packet because there are no more getting called from above. Okay, so yep, stop timer right here. The last point to make is this. When this data packet, sequence number 92, arrives at the receiver, receiver is gonna see, oh, yeah, data byte up to 99 received. But the thing is, the receiver has already received up to 119. So those bytes are extracted and passed up above. So that's not extract 92 to 99 and pass it above again. So this packet will be discarded and an ACK will be sent back. But what is the ACK sequence number? Well, receiver has already seen up to 119. So what is the next byte expected? 120. Good thing is this, when ACK 120 arrives at the sender, well, y equal 120, which equals send base. Therefore, this packet is going to be what? Out of any of the three transitions, we ignore it. Okay, sender does nothing. The second packet here, with sequence number 100 will also arrive at the receiver, and it's saying that it's receiving from 100 to 119. This is going to be ignored as well because, yeah, 100 to 119 bytes have already been passed up to the application layer. So another ACK, 120 is going to be sent back to the sender, and sender is just going to ignore it again. And that was example 3. Up until now, the TCP mechanism we were talking about is very, very simplified. Okay, the examples we went through is very much based on the simplified TCP sender. The actual TCP sender is way more complicated. We have not yet talked about possible retransmissions when the TCP sender receives duplicate acknowledgements. We have not yet talked about extra mechanism in TCP's RDT that supports also flow control and condition control. So these will be coming ahead. But these also, okay, explains in example 3. You'll see in the textbook, the authors will describe it this way. When send base 92 expires, the timer, we only retransmit sequence number 92. But if you recall back and go back in, we will be what? Retransmitting from the smallest sequence number all the way to all packets that have been sent before but not yet acknowledged. So that should include sequence number 100. And that is what I was describing, explaining example 3. The fact in TCP is this. There's something a little bit extra here. When timer for send base 92 expires, the sending window size at the sender there is also reduced to 1. That is saying, when the timer expires, the sender is going to retransmit, but the window size is actually limiting it such that we can only send 1 segment. And 92 is the smallest sequence number, and this is the only packet can be transmitted. And that's why, if you look a little bit careful about the sender's finite state machine we were talking about, and here it is, let's ignore all these other transitions that are not relevant. So we're experiencing a timeout event here. Okay? The description in the finite state machine says this: retransmit not yet ACK segment with smallest sequence number. Now we read down the actions being taken carefully. You see, this is not in the pro form. So we retransmit just 1 segment and then start the timer for that segment. But this is really odd, right? So this is not really like go back in. This is not really like selective repeat either. This is in fact TCP's reliable data transfer mechanism trying to do a little bit of condition control. That's defined more precisely what TCP sender does when there is a timeout event. Know that this is no longer the simplified TCP. This one is actually quite realistic considering congestion control. So in that, step number 1, the window size is dropped all the way to 1. As a result, we are only allowed transmitting one segment, a smaller sequence number segment. And then we're supposed to start the timer, but the timeout interval is set this way. 2 times the current timeout interval value. Then you go, hey, then what was the current timeout interval? Yeah, the current timeout interval is set here and here. In the transition where we get a call from above, at the transition where we receive an ACK packet from below. So you see the timeout interval are calculated this way. Yeah, this is what all those slides were saying, right? This is the equation we came up with. The average round trip time plus 4 times the deviation of the round trip time. Okay. Now, back to the timeout event. Setting the timeout interval to twice the current value. Oh wow. We were actually quite conservative here already, isn't it? That is what? Covering 99.99 something percent of all these RTT samples. And we are setting the timeout interval to twice that amount. That's way more enough. Why? The fact is this, window size dropping all the way to 1 and timeout interval being twice super conservative are both to address the congestion that's occurring inside the network now. Because when there's a timeout, that is also saying there's no more ACKs coming back. That is probably because data cannot go out. But TCP being a pipeline, reliable data transfer protocol, oftentimes we're sending multiple of them out, right? If it's just, a sporadic drop, not due to congestion having consistent drops, then we should still be seeing, maybe a lower number of ACKs, or maybe seeing some duplicate ACKs, old ACKs coming back. Not that we get no ACKs at all and eventually run into timeout. Okay, so timeout is TCP's way of saying that, let's assume now the network is congested. Therefore, let's be very, very friendly to the network. Okay, let's try to slow down. Okay, by reducing the window size, because when the window size is small, you're sending very slowly. Let's also reduce the rate of retransmission, which is to increase the timeout interval. When it's twice that long, then we are retransmitting, the half speed. So both of these extra mechanism is to address congestion, which is to do congestion control. And you see here in TCP, the reliable data transfer mechanism is somewhat mingled with the congestion control. And that's why you see in example 3, supposedly if this is go back in, then when the timer for send base 92 expires, sequence number 92 and sequence 100 should go out. But instead, only 92 goes out. So let's summarize up to this point the similarities between TCP's RDT versus a go back in. So we see similarity being what? Both of them are pipeline segment and both use cumulative ACKs, and there's only one retransmission timer and it retransmits timeout events. We've heard already, unique in TCP is this. The timeout interval is well defined. There's an equation, and there are good reasons just justifying the equation. And we only refresh timer on new ACK. In go back in, we actually refresh the timer even though it's a duplicate ACK. Also, in TCP, that's unique is this. Retransmission, if timeout occurs, we retransmit only one segment. So reducing the sending window size all the way to 1. And the timeout interval is doubled as well. Okay, so exponentially slow in case there are back-to-back timeout events. Now, there are more differences. First one, delay ACK. Second, fast retransmission. So these are the two extra mechanisms in TCP that's related to reliable data transfer that we need to talk about. And what's coming next, a big part, we're going to talk about TCP's congestion control more seriously. All right, so that was slightly complicated, isn't it? Okay, so the next, actually, it are the two extra hacks, the delay ACK as well as the fast retransmission. After we're done with this, then we'll talk about the congestion control. Hopefully, we'll be able to start that today. Okay, we'll see. This is the delayed ACK. So this is the mechanism implemented at the TCP's receiver. All right. Now, in order to contrast TCP's receiver to go backend's receiver, let's bring back go backend receiver's finite state machine. And here it is, the go backend's receiver. There are only two events. First is getting a packet from the network layer, and it's not corrupted, and it's carrying the expected sequence number. Hey, this is the data packet we're expecting. So extract data out, pass it up to the application layer, generate the ACK packet, send back the ACK packet, and then increment the sequence number. So this is in fact the only significant event that we're expecting. All the rest, what the receiver of go backend does is just to send back the same ACK that has been generated previously. And back to TCP's receiver. So the first two events in TCP's receiver are these. Let's read through it a little bit. Arrival of in-order segment with the expected sequence number. Arrival of in-order segment with the expected sequence number. So both are events that's similar, right, to the significant event in go backend's receiver. Data arriving, not corrupted, and carrying the expected sequence number. So good news. We're supposed to generate ACK and send the ACK back. But at the TCP's receiver, okay, how we send the ACK back depends on the second condition here. Okay. So in event number 1, when all data up to the expected sequence number are already ACKed, okay, then we do one thing. If there's one other segment has ACK pending, meaning, hey, that segment there, we should be sending an ACK out, but it's actually pending. We haven't sent it out yet. Then we do this. Okay. Now, some of you might have guessed. Yes, TCP's receiver here is trying to do sending one ACK packet per 2 data packet received. Okay. So, if all data up to the expected sequence number have already ACKed, that's delay sending of this ACK. Okay. So that's wait for the next segment. When the next segment arrives, then we send the ACK. Otherwise, let's just wait for 500 milliseconds. When this 500 millisecond expires, yeah, we have no choice but to send the ACK for this data. So you see here, this is the other condition. When there is a back packet coming in and there is already one data packet that is supposed to be ACK, but the ACK is pending, which means it's waiting for the 500 millisecond. Then we immediately send one ACK, and this ACK here carries the sequence number of the later segment. Okay? And because the ACK is cumulative, so when that ACK comes back to the data center, it's going to clear both this packet and this packet. The third event is more like the default event. Okay, the similarity, however, is more, the action being taken. Okay, so when we receive a segment coming in that is out of order, meaning it's carrying a sequence number that's higher than the expected sequence number, then we will buffer the packet. So as a result, we detect the gap. So let me illustrate so that it's a bit more clear. Okay. Previously, we have received multiple packets, okay, and they are arriving in order. But suddenly, we get a packet that is out of order. It's not quite what we're expecting here next. So there's a gap in the sequence number of the packets received. In that case, upon receiving such out of order segment, upon detecting a gap like this, we send duplicate ACK, the old ACK that has been generated before. This ACK here is then carrying the sequence number of the latest packets received in order. The last event is this. Related to the gap we might see in TCP's receiver. So if a segment comes in that partially or completely fills a gap, then we generate a new ACK. The sequence number in the ACK here will be still the latest packet arrived in order. So this will acknowledge all the packets before that. Last is the fast retransmission mechanism. In order to explain why we need fast retransmission, let's go back a little bit. When we're describing when TCP sender experiences a timeout event, it's what? Dropping the window size down to 1 and setting the timeout interval to twice the current value. Because TCP sender there actually consider a timeout event being network being congested. Now this is very reasonable when there is a congestion. TCP sender here being a pipelined RDT sends often segments back to back into the network, hitting the congestion point. Router there, buffer full, no more space. All these packets arriving back to back gets dropped. Receiver won't be sending any ACKs coming back. Sender has nothing to do but to what? Take the timer that started when we send the train of packets out. And so eventually, timer expires, timeout event triggered, and therefore we slow down very drastically. So congestion, and we slow the sender down drastically, makes sense. But what if the packets go out did not hit congestion point? And we just have a random loss packet in the middle of it. What does the receiver do there? It's going to get packet in order and then, a random loss. All the subsequent packet arriving out of order are going to generate duplicate ACKs coming back to the sender. If you recall TCP sender, when there are duplicate ACKs, what do? We ignore. So sender there will still take the timer and have a timeout event eventually. And we are still what? Reducing the window size to 1 and set the timeout interval to twice the current value. That's overdoing it, isn't it? And that's why we have the fast retransmission mechanism. Because if we see multiple duplicate ACKs, and when there is a heightened number of them, then you will probably guess there is a random drop right before the duplicate ACKs, or at the first unacked segment. So that is exactly what TCP fast retransmission is doing. When sender receives multiple ACKs for the same data, to be more precise, it's triple duplicate ACKs. Then we resend the unacked segment with the smallest sequence number because this is very likely the lost packet there. So then we don't have the timeout interval being long problem, right? Because we'll be waiting a long time to retransmit just this sporadic loss. And this is to exploit the characteristic of TCP being also pipeline. We send back-to-back segments. In case of sporadic loss, non-persistent loss, we could observe number of duplicate ACKs coming back to the sender and resend the packet real quick without waiting for too long. And this example illustrates triple duplicate ACKs. Host A here is the data sender, host B here is the receiver. So window size warrants that we send 5 packets in one train. Let's say packet number 2, sequence number 100 is lost. Then this is going to generate ACK for sequence number 100. But this one is lost, so it's not going to generate anything. All these subsequent packets, it's going to just, trigger the receiver to send the same ACK, back to back. So sender here receives the first ACK for 100. And this is the first duplicate ACK, second duplicate ACK, the third duplicate ACK. And this is when we begin retransmitting the first, the smallest sequence number that is an ACK. And so TCP sender's pseudocode needs to be modified. And the only part needs to be modified is this event, when we receive an ACK packet from below. Okay. First of all, we extract the sequence number in the ACK packet. And this is the case when the ACK packet is new. And this is the other case when the ACK packet is not new. So in here you see, we increment the count of duplicate ACKs. For each duplicate ACK, we increment this by 1. When the count for duplicate ACK is exactly 3, then we resend the segment. So this is fast retransmission of a lost packet. And then of course, drop the count back to 0. This is the last slide to summarize TCP's RDT. TCP's RDT is essentially go back in, so the base is go back in. But TCP being something that we actually need to implement and seeing running, defines very clearly the equation to derive timeout interval. TCP is also a little bit more performance conscious, so timer will only get refreshed when there is a new ACK. When there is a duplicate ACK, timer does not get refreshed anymore, unlike in go back in. TCP there is also not only doing reliable data transfer, it also does congestion control, flow control, and everything else. Therefore, we see when there is a timeout, the retransmission window is only dropped to 1, and the timeout interval could be doubled. More unique in TCP are these. TCP receiver here is also trying to reduce the effort of sending ACKs. TCP receiver here also tries to buffer that arrives out of order. So memory is required as well as the TCP receiver, unlike the go back in receiver. TCP implements also fast retransmission, so for certain patterns of loss, we get to recover faster instead of waiting always for a timeout. And that takes us to quiz number 18. And this quiz is about the delayed ACK. So this is the receiver part of TCP. Now what I'm showing here is the finite state machine of the TCP receiver. Unlike go back against receiver, we have only 2 transitions. In TCP, we have now 4 transitions to cover all these special cases. Now let's focus on the T1, the first transition. It says this: the condition is when we receive a packet, RDT RCV, and it's not corrupted, and it has the sequence number that we're expecting. Good. But there are actually more conditions we're checking now. First, if the packet does not fill a gap, and if there's no pending packet to send ACK out, then we do the following. Extract data, deliver the data, generated ACK packet. Something is missing here. We now start the timer instead, and the timer is 500 milliseconds long. And then increment the expected sequence number, and then set the pending, a Boolean variable, to true. You probably guess what pending is doing here, that variable. So this is transition number 1. All right. A little bit like the significant transition in go back and receiver. Let's go to transition number 2. That's upper right. Okay, the condition look very similar. The only difference is just the last line. Not filling a gap, but there's already a packet pending, okay, waiting to send ACK. Now, in this case, we extract data. So this is a new packet. So let's extract data, pass the data to the application layer, and then what? Generate ACK. Oh, finally we see UDT send packet. And increment sequence number, and then, changing pending to false. So by now you can confirm pending is what? Is a variable to track whether there's an ACK pending or not. Now once you send the new ACK out in transition 2, we set back the pending to false. Good. So T1 and T2, they look very much like the two two events in the delay ACK, the table that we just saw in the lecture. Now, move to T3. Oh, okay, so this is the non-significant transition in go back in, right? Default, we just simply send whatever the ACK packet that has been generated previously. So this is what? An old ACK, a duplicate ACK, all right? So that was straightforward. And then T4, it says this, we receive a packet, it's not corrupted, carrying a sequence number that is expected. And it fills a gap, okay, in the packets that we are observing receiving. Okay. This case, we extract data, deliver the data up to the application layer, and we generate an ACK. But hey, if you look a little bit closer into the make packet function, we are actually giving it the sequence number of what? The highest sequence that has been observed. Okay, highest sequence that is ACK, and this is for all the bytes arriving in order. All right, so after filling a gap, there could be some bytes that we already received that's out of order, but once we fill the gap, hey, the ACK number that we need to be sending out should go all the way to all the bytes that we received in order. Okay, so highest sequence number, all right. And send the ACK out. Okay, UDT send is called again. And then expected sequence number being the highest sequence number arriving in order, +1. Okay, and then, pending is now false. Why? There could be one packet pending, but if there's a packet arriving, filling a gap, we send out an ACK immediately. So if there's any packet pending now, we should just set it false to restart, refresh everything. Okay. So this is TCP Receiver's finite state machine. Good. Now based on the description, okay, question number 1 is asking, which of these transitions, T1, 2, 3, 4, is delaying sending of an ACK? All right, so that should be straightforward. Q2. Which of these transitions you think will be sending new ACKs? Okay, so ACKs carrying numbers that is new. And Q3. Which of these transitions might send duplicate ACKs? All right, which of these? They are not that hard either, so think about it. The problem, the quiz 18 here is slightly challenging, so let's give it 5 minutes of time, all right? And we'll come back and see what you come up with. Okay, we see team 1 here. Yeah. Team 1's answer is, the transition T1 is the one delaying X. Quite obvious, isn't it? Because it's not calling UDT send, it's not sending ACK. Okay. So this is the only possible transition that's delaying sending of an ACK. Q2, which transition send new X? T2 and T4. Are we? Yeah, because T2 and T4 are both receiving new packets and it's not corrupted. So we're actually generating ACK packet using the new packet sequence number. Therefore, these ACKs are new ACKs. And the only one that's sending duplicate ACKs, repeating sending of ACKs that are previously generated is what? T3. But is that so? Think again. Okay. Rocket, think again. So T3 is definitely the one sending duplicate ACKs because obviously T2 and T4 are not. Think again. Okay, let me give you a hint, Rocket. Think. What if the 500 millisecond times out? So sorry that Polly tries to confuse you by describing T3 that way. So it's sending an ACK that has been generated previously. But you see in T1, we are also generating a packet. What if there are no data packet coming in anymore in the 500 millisecond? Okay, so T2 can also send duplicate ACKs. Yeah, I understand. Because if pending is now set to true, right? Receiving the data, then we'll call T2, and therefore we send a packet. So that transition is gonna send new ACK for sure. So let me give you more hints. Yes. T2 definitely generates a new ACK. T4 definitely generates new ACK. Okay, so, but there's one more transition that might also generate new ACK. So you get Q1 and Q3 correct. But Q2, not quite. There's one more transition that can generate new ACK. Okay, T1 is not sending anything, so it's not sending new ACKs. So which one sends also new ACK? Well, there's actually only one remaining. Yeah, this one is hard. There you go. Very good, Rocket. No, your Q3 is correct. Very good. So Kevin also gets it. Because we have only 4 transitions. Hey, that 500 millisecond will take in case there's no more data coming in. So we won't be triggering T2 or T4 at all. But that is going to time out. We did not define the timeout event here. Why? Because, hey, all the rest is going to go to the default. And default there is sending the ACK packet that is previously generated.
which is in T1. And that packet, unfortunately, is still a new packet. Yes. All right. Sorry for confusing you guys. Good. So let's take a break starting from now. It's 11:11. So we'll resume back at 11. Oh, it's not just ticked. 11:12. Okay. I'm sorry. Is it 11:24? 22. Okay. Just to be clear, let's resume. Okay, 1 and 4. And let me just leave the screen like this. Okay. Okay, guys, let me restart OBS. So the stream is gonna go on as usual. I'm just gonna stop streaming from OBS and then restart OBS. All right, so look like you've got them. The TCP receiver's finite state machine as well as TCP sender's finite state machine. So that's actually more realistic how TCP's RDT work. And we now move on to try to wrap up section 3.5, which is pretty long. The rest is actually not about reliable data transfer. It's more on the flow control and the connection management. They're actually relatively simple and straightforward.
And that takes us to the flow control of TCP. Allow me to explain. Okay, so this is again the protocol stack. This is the application layer, transport layer, and the network layer. And packet is coming in from below like this. So network layer is going to pass the segment to the TCP receiver right here. Okay. If everything is okay, TCP receiver is going to extract data and pass it further up. Okay. What's going on really in the implementation in the operating system is this. That data does not go directly to the application layer process. There's this place here called the receiver buffer. So the packet being extracted is actually temporarily stored here, okay, waiting for the application layer process to fetch it. So the application layer process is going to remove data from the receiver buffer. Just like the TCP receiver here is going to push more data into the receiver buffer. Okay. And TCP flow control is needed when the application is drawing data slower than TCP receiver there, delivering data up. Because when that is the case, the buffer space will be what? Occupied. More and more and more and more. Because outgoing slow, incoming fast. And eventually the space is going to be exhausted. The subsequent data will be dropped right there between TCP receiver and the receiver buffer. And this is super bad because TCP here is working very hard to try to get this packet in. Okay. So flow control there is this. For the receiver to tell the data sender, slow down a little bit so that you will not be overflowing the receiver buffer by transmitting too fast, too much. And the way flow control works is this. It works by tracking this variable, RWND. Okay. In the operating system, there's this receive buffer. This is well defined. And it's actually the size of the receive buffer space. Okay. Now, initially, RWND is going to equal the receiver buffer. Whenever TCP receiver sends data to the upper layer, this RWND is going to be subtracted by the amount of bytes being passed up here. Whenever the application layer processes drawing data out of the buffer, the RWND is going to be incremented by the number of bytes there. So RWND is essentially tracking this, the free buffer space. So once we manage to track the free buffer space, TCP receiver here will advertise the free buffer space by including RWND in the receive window field in the packet header, in the TCP packet header, and send it back to the sender. And that's when sender knows it needs to limit its sending window so that it's smaller than RWND. So you see here at the sender side, the sending window not only is limited by the congestion control mechanism, but also by flow control mechanisms, RWND. And that guarantees the receiver buffer not being overflowed. So, receive buffer here, in most of operating systems, when you create a socket, it's set default to 4096. But most of the modern operating systems these days will actually give you different receive buffer space by default. If there's more space, then this is potentially higher. Okay. Last is the connection management of TCP. There are two parts. First is establishing connection. Second, breaking a connection. Let's talk about the process of establishing connection. It needs to be done before exchanging data, and the process is called a three-way handshake. Okay. At the end of the process of three-way handshake, we would establish a connection, or aka a socket. Okay. So once the socket is established, two ends can begin sending data to each other. So the socket establishment process is also exchanging some number of parameters. Now this is crucial because later on, when the client over here on the left is trying to send data, in the packet header there, it needs to carry a sequence number. When that packet arrives at the receiver, which is the server, the server is going to examine the sequence number in the packet header to decide whether to extract the data out and pass it up to the application layer. And when do we extract the data? Only when the sequence number equals the expected sequence number. Okay. So there is a certain parameter at the receiving part, that needs to be initialized. And because either side can be sending data, receiving data, so server here would also need to tell the client what is the initial sequence number server will be using. Therefore, the client can set the expected seek num accordingly. And this illustrates the three-way handshake. Client, server, both initially just listening, and client at some point wanting to request some data will then initiate connection, dial into the server. So it's gonna choose initial sequence number to tell the receiving of the request messages, and it's gonna be sent in a TCP sync packet or sync message. Now, if you recall back in TCP packet format, in the header part of it, there are a number of these flags one can set. So sync packet is the packet with the sync flag being set, the S flag being set. That is also called the sync bit. So that bit is going to be turned to 1, and the initial sequence number is going to be in the packet somewhere. And that packet is going to arrive at the receiver, which is the server. So client, after sending the data, is going to be in the sync packet already sent state. Now the server will then in the sync received state. So server here will be doing two things. First, send back an ACK, to tell the sender of the sync packet that the sync packet is received. So sync ACK is such a packet. That is to ACK, receiving the sync packet. The server here will be doing yet another thing. Choosing its own initial sequence number, and let's say it's Y, and this Y will be stored somewhere in the sync ACK packet as well. So you see here, this packet goes back, and the sync ACK packet is going to have the sync bit on as well as the ACK bit on. And in sequence number, server tells the client it's going to start from Y. And this being an ACK packet is going to tell the sender of the sync packet that, hey, the next one I'm expecting is X plus 1. So next seek num is already set to X plus 1. And lastly, when the client receives the sync ACK back, so it's going to receive the sync ACK. At this point, the client is sure that the connection is established. And so server is live. The last thing the client needs to do is just to acknowledge receiving the sync ACK. So it's just an ACK packet, and the ACK number is Y plus 1. Because this guy here observing the initial sequence number of the server is Y, then therefore the next seek num is set to Y plus 1. And that number is also shown in the ACK sequence number. And so server finally receiving the ACK is sure that the client is live and the socket is now complete and in the establishment state. The closing process is actually not exactly three-way. It's actually independent. The client can initiate the closing process. The server can also initiate the closing process. And the message exchange is just a pair of fin and ACK. So a fin packet out from the one who wants to close, and ACK will come back from the one receiving fin. Right? So there could be simultaneous fin exchange between the client and the server. So the client and the server are both exchanging data. And finally, the client here says, okay, I've finished sending all my data requests, so I'm ready to close. Okay. Then it's going to enter the no longer send but can receive data state. And that is called the send fin, and now wait for the rest of the data to come in. So you see here, the fin packet is the packet with the fin bit on. Server here receiving the fin packet sends back an ACK. Okay, so ACK bit on and then ACKing the sequence number. Server here will enter the close wait. So server knows now that the client wants to close, but it's not quite yet closable because client setting close is just that finishing sending request. There could be some more data waiting to be sent here. Okay, some more ACKs waiting to come back here. Okay, so server needs to finish all these other data that's remaining. But client here receiving the ACK for the fin is pretty much done and just waiting for the server to say everything is already sent, so you're okay. So finally, server says done with all the data. Okay, so sending fin. Client here is receiving the fin, sends back the ACK. Okay, saying good. That's close. Server can now close safely, no problem. But the client here needs to wait 2 maximum segment lifetime before it can really close. And this maximum segment lifetime is usually 60 seconds long. Can you guess why? Why the client needs to stay so long until it can really close the connection? Thank you, Pei-An. Yeah, good. So I know that I need to have your feedback here. Good. So let's start from problem 6. Let's go over the technical materials all the way to the end before coming back to the golden problems. So 6 is asking which of these subnets in the micro internet are edges and which of these are the cores. All right, so that should be quite straightforward, and most of you get the problem right. Number 7. Okay, so this is actually an old exam question.
This is asking you to compare packet switching and circuit switching. So which one would give contention into the network? Only the packet switching one. So this is not characteristic of circuit switching. Congestion, this is also the characteristic of packet switching. Idle resource, this one, however, is circuit switching, because circuit switching does reservation. So if the users are not active, then the resource is left idle. Yeah, it's reservation-based circuit switching. You need a call setup time before we can actually send data. And yep, it guarantees delay to some degree. Okay, so we should have C, D, E, F here for problem 7. Now, problem A should also be straightforward. This is asking the layers we have from the top to the bottom. So overview is the first chapter, not the layer. Application layer, we do have this. Session. Now, if you Google on the internet, because the exam is open internet, so you might see, okay, certain reference documents might say in the original OSI model, session is one layer, and it's actually in between the application and the transport layer. Okay. Now, more recently, we stopped talking about the session layer because there are not really any protocol defined running in the session layer. But if you think a little bit, the TSL, the transport layer security support, okay, transport layer security, so TLS, that protocol should probably be in the session layer because it's not quite for the application and not quite for the transport layer. Okay. And transport layer service, you know, and the next should be the network layer. Now, some of you guys actually missed the link layer. Okay, so there's a link layer before the physical and the network layer. Now, the benefits of doing this internet protocol stack in layers are these. Okay. It's easier to discuss, so we kind of classify the protocols based on the functionalities. Okay, and some would be at the edge. So, yeah, application layer, transport layers are at the edge. Okay, but starting from the network layer down to link and physical, they are going to go into the core of the internet. Now, the link layer and physical layer, however, although they involve these links in the core of the internet, but they are also, okay, edge. So link and physical layer, somewhat both core and edge. So this is for the ease of discussion, and it's also for the ease of maintaining the internet protocol stack implementation. And if we want to evolve and improve certain protocols, it's also easier. Why? Because changing the edge machines, so transport layer, application layer protocol changes will be easier to do. Okay. Now the network layer protocols, because they're implementing these routers in the core, and there are so many of them. In order for these core routers to work together as a whole, if we bring one down, the others will have trouble running correctly. So it's actually hard to take all these routers down and then change at once. Okay? And that's why later on in the next chapter, you hear we do have 2 versions of protocols in the network layer. It's called the IPv4 and IPv6. And we're taking already 20 years to try to evolve from the IPv version 4 to IP version 6. And hey, we are not seeing an end of it. Okay, that's already 20 years effort. Okay, so it's actually very hard to make changes in the core of the internet. And drawback, yeah, there's an initial learning curve, right? Because we kind of need to know which protocol belong to which layer in order to find out how it's defined and how it works, to find references on how it works. Okay, the performance will also be suboptimal because then you can not really do cross-layer optimization. Sometimes if you know a little bit of the lower layer mechanism, and if you tweak it a little bit, then it'll be easier to tweak also the higher layer together. They will work better. Okay. So that's problem 8. And problem 9. Okay, so oops. Problem 9 is a problem that talks about, okay, asks you about the complexity at the edge. Okay. So yeah, simply it's just to push complicated protocols to the edge, okay? Or to push the protocols in the future, we might want to add more functionality into the edge, okay? So pushing functions that is growingly complex or that is yet to evolve to the edge. So meaning at the transport layer or the application layer. And the benefit of doing this is this. So that, hey, you heard earlier, okay, we could upgrade these functionalities easier as long as they're at the edge, okay? We just need to push, we just need to ship the improvements, the upgrades, together with the OS updates. So once you guys updated the OS, those get changed altogether. Okay. Similarly, if this is application layer protocol, once you update the version of the apps you are downloading, then hey, the protocol gets updated. Okay. So we don't need to reboot the code, bring down some of the routers, and make changes there. All right. Another reason is also this. Therefore, the core of the internet, these routers, will be also straightforward, simple. Therefore, they can work reliably and runs really fast for the functionality that's necessary to be implemented in the core. And we actually talk about complexity at the edge, okay, when we were talking about DNS, because name, IP address, lookup, it's actually a very fundamental functionality. All the applications need a function, okay? So why is it at the application layer, right? It sounds like it's common, okay, for all these applications. And it could be also something that the network layer, routers might also ask for. It's a service. That's very, very general. One could actually implement it into the network core, okay? Not necessarily in the application layer. Now, when DNS, such a function that can be both implemented in the core as well as at the edge. Now we try to push it such that it's at the edge. That's what complexity, the design principle meant. Okay, let's push those functions that cannot avoid that can be avoided being in the core. Let's push it to the edge. So that was problem 9. And then, okay, 10. Yeah, so this is the problems that many of you guys have trouble with. So this is talking about HTTP and the connection modes. So the basic mode is non-persistent connection, and this is in version 0.9. Okay, so the time it takes to download an object is 2 round-trip time plus the transmission time of the object. Okay, now, for simplicity, let's just assume that the objects are all the same size. Therefore, Tx is the same, all right? And let's assume also that all the servers to the clients, the round-trip delay is the same, all right? So now, if we are downloading a page that contains 1 base HTML object and 10 additional embedded objects, so this is the same example that Polly tries to use explaining the response time for different connection mode, non-persistent HTTP versus the persistent HTTP, all right? Now, the total response time for the non-persistent connection HTTP will be what? 22 round-trip time plus 11 transmission time. Because for the first object, the base HTML object, it's going to be 2 round-trip time plus ATX. Now for the other 10 reference objects, each would have another 2 RTT plus TX. So altogether, 11 of 2 RTT plus TX. So this is what we get here. Good. But the problem is asking you this. If we're using the modern HTTP, which is 1.1, version 1.1, what this version of HTTP does is it uses persistent connection with pipelining. So that is what we were saying here. Okay, persistent HTTP. Okay. And the delay is going to be different. Okay, response time is going to be much lower. All right. So depending on how widespread the objects are. So in the example we were talking about in the lecture, we assume all the objects are actually at the same machine. Okay, so The delay there is how much, if you recall. There's one round-trip time to establish the TCP connection, another round-trip time to get the base HTML so we could parse the base HTML. Therefore, we see 10 more objects. Therefore, we download the next 10 objects pipelined. Okay, so that's one round-trip time just to get the rest of the 10 reference objects in. So altogether, okay, the page response time to get the entire page down is 3 round-trip time plus 11 transmission time. 1 connection establishment, 1 to get the base, and another 1 round-trip time to get the rest of the 10 objects. Okay. To get the first base object, 1 TX, to get 10 reference objects, another 10 TX. So altogether, 11 TX. Now this problem is relatively, this part of the problem relatively easy. Most of you guys get this one right. What gets complicated begins from the second part of the problem. Okay, so total page response time when the main HTML and 5 of the embedded embedded objects are in the same, in one. Oh, okay. No. The problem was this: the base HTML, 5 of the reference objects, and another 5 of the reference objects. What if they are in 3 different servers? Okay. Now, for 3 different servers, then you need to establish 3 different connections. So for the main file, okay, you establish 1 connection to get the main file, and that will be what? 2 times RTT plus transmission of the base object. The 5 reference object, if it's in a separate physical server, that's 1 round-trip time to establish a connection, another round-trip time to get the 5 objects. And there's another set of it in another physical server, so 1 round-trip time to establish connection, and another round-trip time to get these 5 objects down. Okay, so, and they need to be running in sequence because the assumption is that the client can only have 1 connection to the rest of the world. So 2 round-trip times, 2 round-trip times, another 2 round-trip times to make sure that we get all these objects from 3 different physical servers. So altogether, 6 round-trip times. Okay. And the number of objects we need to download remain the same, 11. Therefore, the transmission time is always 11. Okay. Now, part 3 is asking, okay, so the main HTML and just 1 object being in a separate physical server, but the rest of it, so the other 9 being yet another physical server. All right, so what would the time be different? Actually, no, right? Because the total number of objects we need is 11, so transmission time is still 11. Okay. Now, what about the round-trip time we're spending there? For 3 different servers, yeah, 3 different 2 round-trip times required. So 6 RTT here again. So you probably guessed the amount of time, number of RTTs required is definitely related to the number of different physical servers that are involved. Okay, so problem 4 here, is trying to help you think. What if all these objects, 11 of them, are scattered around 5 different physical machines? Right, so 2 round trips times for each server. Okay, and the first one definitely goes to the base to get the base object, so you get to see the rest of the 10 reference objects. Okay, and so you get 5 of these 2 RTTs in the end, and still 11 TX. And let's see, part 5. Yeah, what if we go the other extreme, right? All these 11 objects in 11 different physical servers, then you get 11 round-trip times. And this is exactly what the non-persistent connection mode is doing, because it's treating that all these objects are in different machines, establishing a connection independently. And let's see, problem 6 here in... okay, so I'm asking you to derive using general terms K and N to come up with the response time. So you see here, if there are n physical machines, then you need 2n round-trip time. Okay? And if there are k reference objects, then the total is k plus 1 transmission time. Okay. Now, problem 7. Okay. For a frequently requested page containing multiple embedded objects. Ooh. Okay. And you know that some of these objects are all scattered around on the internet. Would you rather copy them, okay, locally, or just go to this remote sites repeatedly? Or if you want to reduce the response time, you want them to stay on the same machine. Okay, so just like problem, the first part of the problem, if all the objects are on the same machine, then the response time is going to be the shortest. Okay, so copy them over locally so we minimize the page response time. Okay. Now some of you come up with other answers to justify and the reasons to justify your answer. So it's okay, take your pick, and as long as you can explain why. All right. And that was problem 10. Okay. Problem 11. Okay, so this one is actually quite straightforward. The subproblems that's actually many of you that missed the subproblem that I missed the most are the 5 and 6 here. Okay. So type A, very straightforward, isn't it? Those are the entries containing name and IP address mapping. Okay, so B and EF are the type A. MX is the mail server mapping, so that is domain to mail server mapping. So only A entry is the MX entries. NS are what? The authoritative name server entries. And these two are Google defining the DNS server, the authoritative DNS servers. So C and D are type NS. There are no canonical name entries in the example here. And then 5. Yeah, which of these entries are stored in the .com TLD? Well, you know, right? You know these entries. CD needs to be in .com TLD. Yeah, because that's how you get answers from the .com TLD, who are the authoritative DNS servers of Google. But you know what? Your local DNS server is yet to find out what is the IP address of ns1google.com. And who does your local DNS server ask for the entry from? Yes, yeah, the .com TLD server as well. So all these 4 entries, the IP addresses of the authoritative DNS servers would also be stored in the .com TLD servers. That's why they are all here. And I think it's in page 82. Yeah, page 82 here. Oops, sorry, 84. Yeah. So in page 84 of chapter 2 slide, okay, we actually went through this example. What if you want to start a new company? Okay, you need to install certain entries in your authoritative DNS servers, but you also need to add some entries into the .com TLD servers. Okay, so we add for your domain, who's the authoritative DNS server, the name of it, as well as the IP address of it. So CDEF here. And who are the entries being stored in the authoritative DNS server? Yep, the mail server and the IP addresses of the mail server. So you see here, in the authoritative server, you need to store a type MX record as well as the IP address of the MX, the mail server. Okay, that's why we have A and B both in the authoritative DNS server. Now, problem 12. Okay, so problem 12 is very open. Okay, 1, 2, 3 here, no matter what you say, it's gonna, you're gonna get the credit. And 4, many of you just come up with something that's very intuitive, very simple. Hey, as long as it chooses whatever the problem 1, 2, 3 gives, then you get the credit. Okay. And so 5 and 6 is just simply saying that, hey, if I give you yet another scenario, A, G, F being the option, okay, which one would you pick? Then some of you might see that, hey, you don't get a good answer here. Okay, the final answer is not that good to you. Okay. So in that case, you might justify what is a better approach. But some of you actually find that the answer you get for problem 5 there works pretty well. All right, so straightforward. So then your algorithm in problem 4 here is actually a good design. Okay, so problem 12, the problem set, is actually trying to show you that what people go through in a design process. Okay, so if we want to come up with an algorithm such that the CDNs can choose the right CDN server to serve the video. Okay. Now, those who don't feel comfortable with the answer in part 5, then we will need to readjust the design. Okay. Now, actually, one of the students gave an answer that is actually very, very interesting. So he was saying that, hey, I want to check how the users feels when you have short delay and big bandwidth here, but with a lot of variation. Because in this example here, I'm not just showing you that there are scenarios where you have low average delay, high average throughput, a high average bandwidth, but there's also variation. Okay? Some of you also feel less comfortable when you see high variation connections. And you're right, actually human beings don't like to see a video that actually has a fluctuating bandwidth, or a fluctuating throughput. So actually 12, you guys get pretty high credits for the problem set actually. Oh, and problem 13 and 14, this is actually a set together. 13, very, very straightforward. All you need to do is just to calculate the ones complement sum. Okay. And it's quite straightforward. Once you compute for the first one, you probably see for the second part and the third part, they are all probably 0. Okay. Now, 14 is slightly trickier. Okay, so this is for you to discover how one can come up with a pattern such that it differs from the original data, but yet passing the UDP TCP checksum. It's actually not that hard to find a pattern. So what I'm listing here are some 5 patterns Poly has discovered. You can actually see a lot more possibilities now once you walk it through. Okay. So for example, in Poly's answer 2 to 5, you see that only 2-bit flips actually very likely to happen. Okay. It's actually very easy to have 2-bit flips. Okay. In these cases, you already have a failed UDP TCP checksum. Okay. Now, however, these flips, if you see part 3, okay, so this is the 4th bit in the first 16-bit set, and this is also 4th bit in the second 16-bit sequence. Okay. They have to happen at the same time, at the same position, in order for this sequence to be not detected as an error. Okay. So yeah, having 2 bits, 2 flips is actually very common, but having the flips at the specific positions, that is also somewhat hard. Okay. And that is why I talked in the lecture and maybe in the post in the Facebook group that after some time, the probability running into these situations is low, but we're sending also a lot of data. So probability of running into these is not exactly low. The amount of time it takes to run into these is not long. So for some users, if you are downloading long files, okay, you do additional check. That is actually at the application layer. You do an MD5 check or a CRC check. Now, you don't know MD5 yet, CRC check yet, but these two are just like these UDP TCP checksums. It's actually a coding mechanism. And in a way, we're doing extra coding at the application. We code the file. So once we trans the file, we also send the code so that the receiving side of the file can check also at the application layer where there's any problem. And then 15 and 16, I see. Okay, so these, some of you didn't get many of these problems answered. Many of you actually left them empty, mostly because the exam is actually very, very long. So this is mainly why. So what I want to go through are just these. Okay, the last part of the problem set. So problem set 15 is asking you to show the transition sequences given different scenarios. All right. And last one is asking, okay, can you describe two scenarios that will cover T10? So T10 is right here to the left. So this is the case when you when you receive a packet that is corrupted, okay, or it carries a sequence number that's not quite expected. So this could be what? Scenario 1, yeah, when the packet is corrupted. All right. So this is packet 0 coming in, but it's corrupted. Now the other is, yeah, packet 0 being accepted, and ACK1 comes back, but the ACK1 is corrupted at the sender. Actually, no, ACK0 has already been sent to the sender, sent to the data center, but ACK0 is corrupted. So sender there is resending packet 0. So resending packet, oh no, sorry, my answer is not quite right here. So I should be setting, yeah, ACK1 here and ACK1 here. Yeah, and packet 1 here. Right? So because this is data, packet 1, okay, being ACKed. Okay, so we're here waiting for packet 0. So ACK1 has already been received earlier and ACK1 being sent. But ACK1 is being lost at the sender side. Therefore, packet 1 is retransmitted. Okay. So we receive packet 1 when we are expecting packet 0. All right, so triggering transition 10 because we need to transmit ACK1 again. All right. Now 16, yeah, that's bypassed all these different scenarios because once you see the solution here, you guys figure out what you're missing. Okay. The last part 6. Yeah. So one can actually extend T2 here. So T2 is this one over here. Upper right in the sender's finite state machine. So what we're doing there is when we run into a ACK that is corrupted and the ACK is carrying sequence number 1, we do nothing. Now, what we can do is, of course, to try to what? Retransmit the packet right there. Okay, that would actually lower the retransmission delay. So benefit of doing that, lower the retransmission delay. But in the class, we also went through an example, right? If this is a premature retransmission, then what? We get into persistent duplicate data, persistent duplicate X being sent. Okay? And this is going to go on for the rest of the connection. So the drawback of this is having multiple retransmissions that are useless. Right? So this is problem 16. Let's come back to the Golan. Yeah. Let me walk through the code and you'll see what is tricky there. So in the main of midterm 1 here, so we actually start the listening socket and then the client dialed up and we accept the request and then establish yet another socket. This is the data socket allowing us to send messages. Okay. Now we are deferring closing of the listening socket. Okay, so LN here is the listening socket. But, hey, normally we would have what? Defer? Yeah, closing of the data socket, but we actually neglected defer here. So what I'm asking you in problem set 1 is, what's going to be the output of this midterm 1.go? So, hey, if we close the data connection right here, what will happen? Yeah, the connection here is actually null. So buff new scanner here is not gonna have a connection really. to allow us to read anything. So this is going to be all bypassed. Okay. Writer, of course, having no connection, all bypassed. Okay. So therefore, we will not be receiving any messages from the client and not sending any messages back to the client. So in the end, all we have is just the server printing, launching server. Okay. Client there is simply saying that, oh, I just sent a string of 30 bytes and not receiving a feedback from the server. All right, so that line, close the CONN there, close the connection right there, and all these lines afterwards are bypassed. Similarly, the connection is closed, the client will not be able to receive messages, therefore not printing more messages. Okay. But on the other hand, in midterm 2, so what we're doing here is not deferring the closing of the listening socket. But you know what? We have already started the data connection, and we did defer the closing of the data connection. So the rest of these can go on. The only difference is just that the listening socket is already closed, and if we get another call, there's no way of starting it. But it's okay because midterm 2 here is just taking one request and then closing. So there's not going to be any difference here. Okay, if we close the listening socket earlier or later. And let me go a bit faster here because we have only 2 minutes left. Midterm 3 here. So this is actually asking you the differences of doing go here, okay, in the code midterm 3.go. All right, so sleep here, sleep for 10 seconds. But hey, we do what? Go, isn't it? Wait, let me see. Yeah, so we're gonna get calls, okay, from the client and establishing the call, and then entering handle connection, okay, printing the message, okay, that we receive a message, and then time sleep, okay. But you know what? This is concurrent execution because we are calling the goal. So the sleep there is going to go back into the background. This is going to be a separate thread, a separate process running. So if we get another call there, we're going to start another data connection and call the handle again. The second one is going to print the message and then go to sleep, okay. And the 2 connections are going to be executed, printing the messages real quick. So the delay between 2 responses is going to be very short. The time gap between 1 hello and 2 hello, very small. As opposed to the other one, midterm 4 here, yeah, this is the version without the go. Okay. Therefore, between the 2 calls, yeah, we wait a long time, which is about 10 seconds. And so the difference is simply the reason being, yeah, this version here is not concurrent, and the earlier version is concurrent, having the goal here. Problem 5, okay. Problem set number 5 over here. Okay. So this is asking you, which one would you pick, okay, if you are a user? And the second one is, if you are a service provider, which one would you pick? So some argue they would rather do midterm 4 if I am a service provider, because then my server there will be using less resource. Because if you do the concurrent version, you will have to allocate memory and have multiple processes running at the same time. Okay. Now, some argue that you would still choose midterm 3 here, even if you are a service provider, because, hey, you want to make your user happy. Okay, so take your pick and justify your answer, essentially. And that unfortunately covers all the lecture time for the second hour. So we'll continue and talk about congestion control beginning next Wednesday. So I'll leave the connection run for a little bit longer and start a Google session in the meantime. So in case you guys want to call in for the office hour. So let me just let the Q&A slide show there and start the Google here. Okay, good. So let me just end the session here, and I'll see you next Wednesday.